Hi everyone, how are we doing? In this video I'm going to go through calculating the moment of inertia, or second moment of area of a shape. Moment of inertia is a measure of the resistance to bending, so we need that for calculating stresses due to bending and also deflection due to bending. So let's have a look at the problem and see how we do it. Okay, so here we have the problem. So we just got this upside down T-shape, and we need to know the moment, or firstly determine the location of the centroid of the shape and the moment of inertia. So for calculating stress and also deflection due to bending, the equations use the moment of inertia, and the moment of inertia needs to be calculated about the centroidal or neutral axis. All right, so first thing we need to do is to find the centroid. So our solution is to use the equation for the centroid, which says that the centroid of a composite shape like this is equal to the sum of the first moment of area of each of the shapes. So it's just the area times the centroid of that shape. So if we've got a composite shape made up of lots of little shapes, we can look up what the centroid is. And if it's just a square or a rectangle or a circle, we know that the centroid is going to be at the center of that shape. Sorry if you can hear that dog barking in the background. Problems with working at home, you get noises like that. But anyway, I can see that that's coming through on the monitor. Hopefully you can ignore that. All right, and then we need to divide by the total area. So there's usually multiple ways of calculating the centroid for a composite shape. So I'll go through a couple of different ways. So the first method is to split the shape up into these two rectangles like I've shown here. So this top one and this lower one here. So we'll just label them 1 and 2 for reference. And because this is a simple regular shape, we know that the centroid of this shape is at the center of the rectangle, and similarly for the one above it. Yeah, so if this is 0.1 high here, then we know that the centroid of this shape is 0.1/2. And similarly for the center of the rectangle number 2, the centroid of that shape is at its center there, and we can easily work out its height from the other dimensions that we're given. So 0.1 plus 0.3/2. Put on our other dimensions there for reference. So starting to now apply our equation for the centroid, we have A1 times Y1 bar, or the centroidal distance to area 1. So we know what that is. Put that into our equation. So we have 0.2 times 0.1, which is the area of this rectangle, times its centroidal distance from the reference axis or the datum. So as we saw before, 0.1/2. And then we have area 2, which is 0.3 times 0.1, and its centroidal distance from the datum is 0.1 plus 0.3/2. Divide by the total area, and we get that the centroid is 0.17 meters above the datum. Now, what you can do as a check for your calculations is, if you think about this, then the centroid of this composite shape must be somewhere between the centroids of the two individual shapes, right? So it must be somewhere in between these two. So if you got a number, so what's this going to be here? 0.1, 0.25. So if you got 0.27, right, as an answer, then you know that that's not right. You've done something wrong somewhere. Or if you get an answer, 0.02, for example, then you know that that's not going to be right either. All right, so that's one way of calculating that, and I've just indicated on my drawing here the centroid of the composite area there, Y bar. So now looking at moment of inertia, so I do the calculation of the centroid in a different way after I've done this, looking at the moment of inertia. So moment of inertia, repeating all of that I had before, just for reference, indicating that my centroid is now 0.17 above the base here. So we'll need that in our calculation of the moment of inertia. And to work out the moment of inertia of this composite shape, we need to make use of the parallel axis theorem. So the parallel axis theorem says that the moment of inertia of the composite shape is equal to the sum of the moments of inertia of the shapes about their own centroid plus the distances to the centroid of the composite shape from the centroid of the individual shapes. So let's put on some axes for reference here. So I'm going to call the horizontal axis X, vertical axis Y. So where we need to indicate which axis we're calculating the moment of inertia about. So, we could calculate moment of inertia about the y-axis, but we want to know the moment of inertia about the x-axis here. And we know for a simple rectangular shape like this that the area of a rectangle is BH. That's pretty obvious. But the moment of inertia, which is of more interest to us for this problem, obviously, is that the moment of inertia, or second moment of area, of a rectangle about an axis is BH cubed on 12. If we want the moment of inertia about the y-axis, then it would be H times B cubed on 12. All right, so let's see how we put that into practice for this problem. So we've got two shapes here. We've got rectangle 1 and rectangle 2. So the centroidal moments of inertia for each of the shapes is just BH cubed on 12 for each of the two rectangular areas. So hopefully that's straightforward. And then we need to do this sum of the area times the distances between the axes that we're using the parallel axis theorem for. Okay, so in this problem we want to know what the moment of inertia of shape 1 is, for example, about the centroidal axis of the whole shape. So the distance between the centroids here is what we need to put in this equation here. So d1y will be the distance from centroid of shape 1 to the centroid of the whole shape. And then for rectangle 2, the area is just B2H2, and then the distance that we need is this distance here between the centroid of rectangle 2 and the centroid of the whole shape. So if you put in all of those values, so here for rectangle 1, this distance here will be y bar, so the centroid of the whole shape minus the distance to the centroid of rectangle 1. So 0.17 minus 0.1 over 2. And that's all squared. And then for rectangle 2, the area is 0.1 times 0.3, and then the distance between the two centroids here, so y2 bar here is 0.1 plus 0.3 on 2, which is what we've got here, minus 0.17. Make that all squared, and we get our moment of inertia. So 7.217 by 10 to the minus 4 meters to the fourth. Hopefully that makes sense. So let's have a look now at a second method. So method 2, what we're going to do now is to look at the shapes as one big rectangle encompassing the whole area, and then subtract these two rectangles on the side, on each of the sides here. So you can apply this equation to shapes where there's bits cut out of the side like this one, or where, if you've got, you might have a hole through there, for example, that you want to cut out. So the easiest way to find the centroid of the rectangle with a hole in it is to subtract the centroid or first moment of area and the moments of inertia of the hole from the big rectangle. Right, so that's what we're going to do here. Subtract these areas on the side for the cutouts. So put on all our dimensions again, indicate our centroids for the simple shapes, for this composite shape. So the centroid of the big rectangle, right? It's just at the center of the big rectangle, and then the centroid of the rectangles on the side that we're cutting out this time is at the center of those rectangles. Okay, so now if we apply our centroidal equation, sum of the first moments of area divided by the sum of the area. So we have the total area here, so the big rectangle, 0.2 times 0.4, and its centroidal distance is 0.4 over 2, which I've got here. And then we're cutting out the two rectangles. So the centroidal distance for these is, so this distance here is 0.3 over 2. So 0.4 minus 0.3 over 2 gives us this height here, y2. Then the area is 0.05 times 0.3, and then multiplied by 2 because we've got 2 of these areas. And we've subtracted these. Right? And then divide by the total area. Again, just 0.2 times 0.4 for the big rectangle minus the area of the two side rectangles here. All right. Put all that into your calculator and we get 0.17, which is the same as we had previously. All right, so it's not a bad idea to do your calculations in two different ways, just to make sure you haven't made a mistake somewhere, just as a check. All right, so I've just put in the centroid here for the whole area. Now, notice this time it's below the centroid of the whole shape. Okay, it's not in between this time because we've subtracted this area. Okay, so if we're subtracting some area, then we should expect that the centroid will be below the centroid of the whole area. If the centroid of the area that we're subtracting is above the centroid of the area that's actually there. Right? If the centroid of the area that we were subtracting is below the centroid of the big rectangle, then we would expect the centroid of the composite area to be above. Right? So it's always good to have, go through these thoughts as a check for your calculations. And not only does it help you to check your calculations, but it also helps you to understand what you're doing in the deeper way, right? To really understand the calculations that you're doing. So if you can do these kinds of thought experiments and checks in your head, then that's indicating to you that you're gaining a better understanding of what it is that you're actually doing and what you're calculating. All right, so let's look now at the moment of inertia. Use the same approach to calculate the moment of inertia. So we're going to use these negative areas, if you like, in our parallel axis theorem. Put on our axes again, a reference. All right, so to start with, we've got the big area, 0.2 by 0.4 cubed on 12 as its centroidal moment of inertia, minus the two negative areas. So 0.05 times 0.3 all cubed over 12 times 2 because there's 2 of them, and negative because it's a negative area or a space in our cross section. So then we have the AD squared part of the equation. So the area of the big rectangle, 0.2 times 0.4. Its centroid is at 0.4 over 2, so 0.2. Distance to the centroid of the composite shape is 0.2 minus 0.17. Okay, so that's what we've got in here, all squared. And then for our 2 negative areas, 0.05 times 0.3, and the distance between the centroid of the composite shape, so this one here, just y bar, and y bar 2 of these negative areas is up here. So this was, what was this, 0.4 minus 0.3 over 2, so that's 0.25. So this distance here is 0.25 minus the height of the centroid of the total area, 0.17, all squared. Do our calculations and we get the same answer as we got before. Okay, so now I'm going to do a check with the software SkyCiv. So let me exit out of here. So I've actually got here the answers, but I'll just go through the check or how to use. I'll just go through how to use that. So you can see the URL there. If you can't see that on the screen, you just type into Google SkyCiv moment-of-inertia-calculator and you'll find it. So for the free version, we've only got a set of regular shapes. Okay, so that's about 8 or 9 there. So we have in this problem a T-beam. So you can see it's in a different orientation to what we've got in our problem, but that shouldn't matter. We should be able to work out what we need from the software and interpret our answers to match our problem. So let me just go back to that. Okay, so there's our original problem. So we need TFW, which is the width of the T. So that's 0.2. Oh, I've got units in millimeters here. Let's make these meters. So 0.2. Top thickness, which is 0.1. Web height is 0.3. Sorry about the dog barking in the background. And the web thickness is 0.1. Okay, so there's our shape. Upside down from our problem, but that doesn't matter. If you pay for UTS students the $10 for the UTS discounted version, then I think you get access to the tool or the facility that enables you to build anything. So you've got down here, build anything. So you can build it as it actually is. So, but we'll just use the free one for now. So calculate that. So it's showing me all this stuff, wanting me to sign up. So click show my results, and we can see our results over here. Okay, so I'm just going to go back over to, so this is what we calculated with SkyCiv. So we need to do a little bit of interpretation of what we've got here. So for the centroid, so the centroid is labelled here with C. Now we have the y-axis was upwards, which is the same as what we had in our problem. So CY is what we've got here, but it's showing us here 0.23, but of course it's upside down, right? So our height, total height was 0.4. So 0.4 minus 0.23 gives us 0.17. Okay, so this checks out with what we calculated for our solution. Now, the other thing that we calculated was the moment of inertia. So in the software, it's got the z-axis instead of the x-axis that we had. So here we need to look for IZ. Okay, so this also indicates, why over here in my solution I took the time to label my axes on my diagram, and then in my equations to put the subscripts to indicate what I'm actually talking about, right? So in engineering communication, you need to communicate clearly about what your solution is, right? And what things refer to. So without this X here, the reader has got no idea whether you're calculating the moment of inertia about the y-axis or the x-axis, right? So you need to communicate that clearly. Right, so back over here to SkyCiv. So we want IZ up here, and we get 7.217 by 10 to the minus 4. Well, that's what we got in our calculations. Does that match? Yep. So go 1, 2, 3, 4 to here. Decimal place between 7 and the 2, so 10 to the minus 4. Right, so that checks out our solution. So that's okay. All right, that's the end of the problem. Hopefully that was interesting and helpful for your understanding of how to calculate the moment of inertia and the centroid, and also how to make use of the software SkyCiv. That's it for now. See you next time. Bye.